Speed and velocity are two ways you can describe how fast an object is moving, and both are calculated in basically the same way, taking the amount of distance the object has traveled divided by the time it takes for it to get there. You can use meters or inches or kilometers or miles for your distance. You could use seconds or minutes or hours for your time. Doesn't make a huge difference as long as you're consistent with your units. If you want to get a little bit more fancy, velocity is technically the displacement of an object divided by the time it takes to get there. So usually shown as a delta x or a delta y divided by a delta t, where that delta just basically means a change in something. Now, we've had some practice up to this point with measuring and calculating speed and velocity, but up to this point we've only really calculated and measured average speed or average velocity, which means we're kind of shooting for the middle. So far, the objects that we've been taking measurements on don't travel at the same speed all the way through their path. So for me to say that this popper travels at, say, 300 centimeters per second is not technically true, because at some points it's moving faster and at some points it's moving slower. And at one point it's not even moving at all. If I flip this popper inside out, build up some potential energy that can exchange into kinetic, it gives it the power to launch up into the air. Ooh. And at some point, it's got to come back down. Gravity is constantly pulling downwards on the popper, so as it rises through the air, that kinetic energy changes back into potential energy, and it slows and slows until it actually comes to a stop for just a fraction of a second, at which point gravity pulls it downwards and it goes faster and faster until it lands. So at some points, it's moving very, very quickly. At other points, it's moving slower or not even at all for a fraction of a second. So I can't just pin one single speed or velocity to a moving object like that. Okay, we see it with the reaction rocket for the same reason. We see it for any object that is sliding, where we have a push to get it started, but it comes to a slow and a stop. And we'll go more in depth into that when we talk about forces. But for now, in order to get a more accurate reading of something's speed or velocity, we're going to look at a few cases where we can actually get something to move at a nice, consistent rate, a constant speed, where whether I let it go for a long distance or a short distance, or I let it travel this way or that way, the speed is the same. If I want this box of paper towels to move at a nice, consistent speed or a constant rate, I need to continue pushing it to keep it going against the friction that is trying to slow it down and stop it. But it's kind of hard for me to be consistent about how fast or slow I push this thing, because I'm a human and I make mistakes. So instead, we're going to use this guy. This is a tumble buggy, and he is perfect at moving at a pretty consistent rate. The battery power that he has helps him to continue to push against friction so that he continues moving at the same speed all the way through his path. And since speed is a rate of distance versus time, whether the tumble buggy goes for a long distance or a short distance shouldn't make a difference in how the speed is calculated. So if I hit this little on switch here, my tumble buggy starts going. Set him there. He starts to move. He can also tumble, move back the other way. Okay. In order to verify that he's going to be moving at a constant speed, and also to gather data on how fast he actually moves, I'm going to measure the time it takes for the tumble buggy to move 1 meter, 2 meters, 3 meters, 4 meters, and 5 meters. And by using that distance of 1, 2, 3, 4, and 5 meters, and the time it takes in seconds, I can calculate out how many meters per second the tumble buggy is going to travel, what its speed is, consistently and constantly through its path. Now, I don't have enough room to do that in here, so I'm going to have to move out to the hallway. We're going to have to use tape marks to show how far our 1 meter, 2, 3, 4, and 5 meter marks are, because I don't have enough meter sticks to just lay out like this for 5 meters for everyone. So let's go do that. The first thing I'm going to do is measure out my 5 meters of distance that the tumble buggy is going to travel, starting with a starting line. I'm just going to put a piece of tape down on the ground to represent that. Since my meter stick is starting at this tape line, I'm going to make this next tape line at the end of the meter stick here. That way, when the tumble buggy hits the starting line, I start the timer. When it hits the next piece of tape, I stop the timer, right at the very beginning here. So from the beginning of that tape mark to the beginning of this tape mark is 1 meter. I'm going to do the same thing for the second meter. This right there. And I'll do this for all 5 meters, so I should end up with 6 tape marks. So 1 for the starting line and 1 for each of the 5 meters after it. Now, I'm going to use a stopwatch to measure how long it takes in seconds for the tumble buggy to travel 1 meter, 2 meters, 3 meters, 4 meters, and 5 meters. You can use a stopwatch on your phone or a laptop. You can use a physical one, doesn't really matter. As long as you're keeping track of the time in seconds, we're good to go. Now, my advice is to not start your tumble buggy right at the starting line when you turn the on switch on, because having to turn the on switch on and hit the start button on your stopwatch at the same time is going to be tricky. Even if you have a partner or a group member that can do one thing for you so you can start the timer at the other, trying to coordinate that can be tricky. So here's what makes it easier. I'm going to start this before the starting line. So that way, when it hits the starting line, I can start my timer, and when it hits my mark for 1 meter or 2 meters or 3 meters, I can stop the stopwatch. Okay, so I've got my stopwatch here. So, start. Stop. About 2.74 seconds. Now to try and get an accurate reading of the time, I'm gonna have to start moving with the tumble buggy to make sure that I see right when it's squared up to the end of that 1 or 2 or 3 meter line, so that when I hit my stop on the stopwatch, I get an accurate read of how long it was actually moving for when it traveled that full distance. Okay? If I'm looking from the beginning, then I might misjudge it. Kind of like how when you're reading a liquid level, you need to be on eye level with it. We need to be on eye level with the end line so we can make sure that we hit the stop on our stopwatch at the right time. Now, if you're, again, working with group members, then you might be able to have someone end at the end line, be ready for it, and then mark it off there. But walking with it is probably the most accurate way to get it. Okay, so here we go. Start. Stop. All right, I've got my time for the first meter and the second meter. Now I need to do for 3, 4, and 5 meters. So here we go. Same idea. Start. Stop. Here's for 4 meters. Start. 1 meter. That's 2 meters. That's 3 meters. Stop. And for 5 meters, make sure that I'm ready on my stopwatch. Okay, for 5 meters, start. 2, 3, 4. Stop. I now have the time for all 5 meters. Now I just have to use the data to figure out how fast the car is moving. And Google Sheets is going to be really good at helping me handle that. So I'm going to put these distances and times into Google Sheets and use that to figure out how fast this car is moving. So I have a problem. How do I trust a combination of a distance divided by a time to get my speed for one trial more than the other. I can't really. So instead, I have to use multiple attempts, multiple trials, to be able to figure out what the speed is, where it's not just this data point that matters, or this data point, or this data point, but all of them. One of the best ways you can accomplish this is by graphing out your data points. I've got my distances on the y-axis and time on the x-axis, and I've placed out points to show how much time it took for the tumble buggy to move this far. 1 meter, 2 meters, 3 meters, 4 meters, and 5 meters. Now, like you saw in my speeds that were calculated in Google Sheets, they're not perfect. They should kind of line up, where if moving at a constant speed, we have some distance per time, distance per time, distance per time. These should be kind of like lining up here, and they're not. Which is not to say that I did a bad job, it's just to say that I, as a human being, sometimes make mistakes. Sometimes I start the stopwatch or stop the stopwatch at the wrong time. Again, not because I'm not trying, but because I'm a human and I have electrical impulses in my brain that are trying to tell me when to hit the button using my thumb that has to move, while I also have to move my eyes and watch and process the information. So all that together means that I'm bound to make some mistakes. But I can average those out in a really fancy way by using multiple data trials, and not just by adding and dividing by the number of trials, but by graphing them out and making a line that shows the correlation between them, how they relate to each other. It shows the pattern or the trend in those data points. So let me grab this meter stick here. Now I could try to connect the dots with these and go straight from one data point to the next, to the next, to the next. But then I'm just including all the mistakes that I accidentally made. The times when I probably hit the stopwatch a little bit too late because I was trying to watch the car and hit the button at the same time. So my eyes pick up the information through light that I see the car hit the stop line, so I hit the stop button, but I have to be able to process that information in my brain to make my thumb move to be able to hit the button. And sometimes I try to anticipate the fact that it takes me a second to register and to hit the button, so I do it a little too early, where I'm trying to expect it to cross the finish line at a certain point, and I accidentally stop it before it actually has. So if I adjust that a little bit, and I kind of go between those mistakes, not trying to hit any specific one data point, I might get something like this that shows the pattern or the trend in these data points by putting a line through them. Okay? Now this trend line would be fantastic at telling me one consistent speed that the car is traveling at by eliminating my errors as I go one way or the other too far. But it's a line. How do I get a number out of a line? Well, you may have seen this in a math class before, but how steep this line is, called the slope, actually does have a number associated with it. It's how far up the graph and how far over on the graph you have to go to hit this line. Not any specific one of these points, this line that I've got best fit to show the trend in these data points. The slope of a line is equal to the rise of the graph divided by the run of this graph. How much we have to rise and then run to be able to hit the line. And in this case, distance on the y-axis going vertical is the rise, and time on the horizontal x-axis is the run. So our rise over our run is distance divided by time, which is speed. So the slope of the line is the speed of the tumble buggy. In other words, if I can tell how steep this line is, what the slope is, that is the same as the speed in centimeters per second or meters per second. In this case, we're using meters per second. So I want to make that consistent with our data. Okay, but it works the same way whichever units you use. Okay? Now, there is a way that you can do this by hand, where you can bust out a ruler and figure out how far you have to go up and over to hit the line. You can do a little y2 minus y1 over x2 minus x1 action to calculate the slope for your rise over run. But Google Sheets can actually do all of this for us. It can make the graph and put the trend line through it and tell us the slope as a number, which is going to be the speed of our tumble buggy, all with a couple clicks. So let's do that. Let's save some time having to make the graph physically and look at how Google Sheets can make that happen for us really easily.